Good morning, everybody. Welcome back. This week, we start learning about potential energy and the conservation of energy. Last week, we discussed kinetic energy and work and how we change the energy of a system, and we'll incorporate some new energy concepts into those same ideas this week. So, potential energy, what is it? You're all probably familiar with the idea that something that's sitting on top of a cliff has potential energy, that energy of position where it can fall down off the cliff and change its kinetic energy. So something can happen. And besides having gravitational potential energy, we can also think about other forms of potential energy, like a wound up spring, a stretched elastic band, or an object at some height above the ground. So this last one is gravitational potential energy. So where does this gravitational potential energy come from? Let's take a look at this box here of mass m, and we're going to lift that box a vertical distance, some height represented by delta h. So the work that we do here is going to be the weight of the box multiplied by the displacement, and in this case that displacement is going to be the vertical height. And so our equation to figure out the work that's done vertically upwards is going to become our equation for potential energy. So the work that we do increases the energy of the system and we gain some gravitational potential. So mass times gravity times height, or y. However, is any net work done in this case? And the answer to that is no. The reason is because gravity is also doing negative work in the opposite direction as the displacement. And so the net work would be the work done by the hand minus the work done by gravity, which would be zero. So how can we have gravitational potential energy? Well, remember the work energy theorem says that the change in net work is equal to change in kinetic energy. And so really, if net work is zero, the kinetic energy did not change here. Yes, we've increased the potential energy, but at the end of the day, if the object is not moving, our kinetic energy value is going to be zero. So one of the coolest things about energy is its ability to be transformed from different types of energy and conserved. And so what we can have here is an object with gravitational potential that can then become kinetic energy if the object is dropped. And we can predict what that kinetic energy will be as long as we don't lose energy from the system due to forces like friction and air resistance. Now, where do we measure the height from? It's always a question students ask. It turns out it doesn't really matter that much as long as we define our y equals zero. So I could talk about the potential energy of myself sitting here at this table above the floor, or I could talk about the potential energy of myself since I'm in the second floor above the ground below me. So it's sort of arbitrary. What do I want to define as height equals zero? Well, usually, depending on your situation, the height equals zero choice will sort of be apparent in whatever you're trying to find out. I mean, we could talk about the potential energy with respect to sea level, but how is that going to help us do energy problems when we live in Helena, Montana? So we can also have potential energy stored in a spring. So when we compress the spring, we know that that took some work to do. I applied a force over displacement, and the work was not net work because the spring pushed back on me and did negative work. So once again, we don't change the net kinetic energy, but we do create potential energy. By virtue of the spring being compressed, there's energy stored there. If we let go, you know something's going to happen. The potential energy of the spring is going to be transformed, the ball is going to be released, and now it's going to have kinetic energy. So all of this potential energy of the compressed spring becomes kinetic energy after the ball is released. And a couple things to know here, the force required to compress a string is given by Hooke's law, which is negative k delta x. So negative k is this value which represents the spring constant. It's a big number for a really stiff spring. It's a small number for a small spring. And depending on how far we compress or stretch the spring, we can store energy. In this case, I'm stretching the spring out, and every spring has an equilibrium position that it wants to be at rest. So in this case, I stretch the spring out, and there's going to be potential energy for it to return back to its neutral position. So probably a more important equation than Hooke's law is the elastic potential energy equation. And this one isn't in your textbook. I included it in the equation sheet for this unit, 1/2 kx squared. So what that means is if I want to calculate the potential energy in joules of a compressed or stretched spring, I would need to know the spring constant and how far I've stretched it or compressed it. And the powerful thing here is we can use this equation to predict kinetic energy when the spring is released. Think about a dart gun. If we know the K value of the spring in a dart gun, we can measure how far that spring is compressed. We can predict the velocity that the darts are being fired at. Conservative and non-conservative forces. What in the heck does that mean? Conservative forces are forces where conservation of energy applies, and non-conservative forces are forces where conservation of energy might not apply, like we might lose energy. So one of the biggest non-conservative forces is friction. So friction is this force that if it's involved, we're sort of losing energy from the system. In a non-conservative force, the pathway matters. The work that's done, if we have a bigger displacement here around this circular path, that distance is bigger and friction is acting the whole time. So friction, if I want to not lose as much energy, I would take the shorter path. But a lot of other forces like gravitational, elastic, and electric forces, the pathway we take doesn't necessarily matter. So going back to the Mount Helena hiking example, because we're going against gravity in that hike and we're not dragging a box of bricks behind us, that pathway we take requires the same amount of energy in both cases. Now, if I did have friction, a non-conservative force is acting, taking energy out of the system, then I would probably want to take the shortest path. If you think about hunting, and maybe you've shot a deer or something like that, we probably would want to take the shortest straight line path from the kill site to the truck. And that's because friction is going to be acting everywhere that you go, and so we want to reduce that distance. Should make sense. So the work done by non-conservative forces is going to take energy out of the system. If only conservative forces are acting, then we do have what's called conservation of energy. And so if there are no conservative forces, the sum of the changes in kinetic and potential is zero. So in the beginning of the day, we have some energy value. We climb a hill, and the energy value is still constant. Wait, how does that work? Well, the energy changes from kinetic energy to potential. And I like to think of energy buckets, and depending on our position, the energy is like this stuff that we can have. It sort of transfers between the kinetic bucket and the potential bucket, but the total amount of energy that you have to have is going to be the same. Take a look at this picture here. This one should help you understand this. The rock at the top, it's all potential energy, right? There's no kinetic energy. We haven't dropped it. Halfway down, the energy begins to transform. Now we have half of the energy in our potential bucket, half in our kinetic bucket. The total energy of this system, though, remains constant throughout this motion. At the bottom, All of the energy is now in the kinetic bucket and the potential bucket is empty, but we still have the same amount of energy that we started with. That is assuming that we have no non-conservative forces acting here, like friction and air resistance. So with air resistance in this short drop, we would have a little bit less kinetic energy than we expect. So one of the big things we're going to do this week is we're going to be doing a lab with, if we get some snow, there's a winter storm watch now. My plan is to do the sledding lab next week. And that's going to involve us figuring out our potential energy at the top of the hill and predicting kinetic energies at the bottom of the hill given conservation of energy, and also be able to predict velocity at the bottom of the hill. We'll go even a step further and include non-conservative forces like friction. We'll actually calculate our frictional force by dragging the sled around and determine the coefficient of kinetic friction. And then if we know the distance of the slope, we can subtract the work done by friction and make a pretty accurate prediction as to the work or the available energy at the bottom of the hill. But that aside, let's take a look at this example. Let's say I have this roller coaster here, bunch of energy at the top, it's all potential, I'm not moving. At the bottom here, it's all going to be kinetic. And if I return to the same original height without friction or air resistance, that's all going to be potential again. If the track kind of flattens out halfway up the hill, I'll have half of my energy be back in the potential bucket and half be in the kinetic bucket. And so what we call this is conservation of energy, and the total energy of the system remains constant. Take a look at this one here if you're interested with pole vaulting, and that's a storage of elastic potential, changing it to gravitational potential for interest. I'm not going to talk about that one. And I think we're almost good there. Energy conservation with dissipative prosody. It's dissipative. Okay, so let's talk about this really quick before we finish this up. I have 2.5 minutes. Let's say that we have an initial kinetic energy, object on level ground, and the object rolls and comes to a stop, like we know is going to happen. So in that case, energy is not conserved. We're going to think about this dissipative process where work is removing energy from the system. So what happens here is the original kinetic energy that we had goes to zero. Well, the work that's done, or the dissipative force, is going to be the force multiplied by that displacement doing work in the negative work to take energy out of the system. And you can figure out things like what's the magnitude of the air resistance using that strategy. Sort of like we did with the Rolly chair lab with impulse and momentum. The difference here is that instead of thinking about impulse in our time interval to calculate the force, here we're thinking about the displacement to figure out the force. But very similar concepts, the work energy theorem and the impulse momentum theorem. Okay, conservation of energy. Good luck.